We're pleased to have the next talk of the day by Yael Shadmi, and she will tell us about on-shel Higgsing and standard model EFT.
Hi, so thank you, and thanks for the opportunity to talk here. So I'm going to be talking about a few papers with my student Yaniv Weiss, Gautier Durier, who's now a postdoc at CERN, Tepe Kitahara, who's at Nagoya, Camille Machado, who's at Daisy, and Reuven Balkin, who's a Technion postdoc now. So the main goal in this talk is going to be the construction of massive EFT amplitudes. Namely, what we want is a set of independent endpoint massive contact terms. And I'm going to discuss two approaches to this. One is a bottom-up approach, where I'll be fairly brief, and then a top-down approach, where what we're going to do is start with the EFT amplitudes of the unbroken theory, namely the set of independent massless contact terms, and sort of Higgs these on-shel to get the massive amplitudes. So let me start with a bit of motivation for why effective field theories, or why effective theories, and why on-shel. So where are we in terms of electroweak symmetry breaking? We have a very nice parameterization of electroweak symmetry breaking in terms of the standard model Higgs mechanism, but it's completely ad hoc. We don't know why there is a breaking. We don't know where the scale comes from, how it's stabilized, and we don't know whether naturalness is dead or alive. So it's very sensible to turn to a bottom-up approach and do precision measurements of the entire electroweak sector at the LHC. And effective theories give us a well-defined framework for interpreting these measurements in a way that's quite model independent. Of course, it's not completely model independent. There are different possible standard model EFTs that you can think about, whether it's the standard model only or the standard model plus some other fields, whether electroweak symmetry is realized linearly, is the Higgs part of an SU2 doublet, as in the SMEFT, or is the symmetry realized non-linearly? So an on-shel approach is very natural when you think about EFTs. After all, when you talk about an effective field theory, your input are the standard model fields, possibly some new fields, the standard model symmetry, and of course, Lorentz and locality, and out comes the most general Lagrangian consistent with all these assumptions. And this is very well suited to a bottom-up on-shel approach. So here the input is the standard model particles, possibly some BSM particles. Again, the symmetry, only this time you really just need to impose the global symmetry, and Lorentz and locality, and out come all the possible couplings, the 3 points, and all the contact terms, higher point contact terms. And then you can sort of put these together to get the full amplitudes to whatever order you're interested in. Now, the first step of an EFT construction is to identify a basis of operators. So you want a complete basis of independent operators, modulo the field redefinitions, gauge redundancies, integration by parts, equations of motion. So this is a very complicated problem. It was beautifully solved using the Hilbert series in a series of papers, but it really becomes much simpler on-shel. On-shel, you only deal with physical quantities. There are no issues of field redefinitions. And essentially, the problem translates to finding basis of independent contact terms, namely independent Lorentz structures that are manifestly local. And so this is much simpler than thinking about a basis of operators. Also, working with physical observables only, if you work in the low energy theory, in principle gives you a much easier comparison to experiment, or more transparent comparison. And the reason is that the EFT operators usually shift all the masses, standard model couplings, and everything else once you go to the broken phase. So all your input parameters need to be redefined. Now, when we talk about on-shel EFTs, you can work either in the high energy theory or in the low energy theory. And my high energy theory is not terribly high in this case. When I say high energy, I mean above the Higgs VIP or above the electroweak scale. In this case, you're talking about the unbroken SU2 times U1 with massless amplitudes. Or you could work in the low energy theory below the VIP, where the symmetry is broken. In this case, you're talking about massive amplitudes that involve both the massive and massless standard model particles. Now, I'm not going to talk very much about the high energy amplitudes. They're obviously a good approximation for many LHC processes, and they're all you care about for thinking about running anomalous dimensions and to some extent positivity. And there have been many results on the standard model EFT and other EFTs using on-shel methods. So these include the classification of operators in various theories up to dimension 9 in the standard model EFT. There are results on anomalous dimensions, the mixing and unmixing of different operators, and there's a really impressive set of results by now. I'll mainly talk about the low energy theory. And here we can take an approach that's completely bottom up. So working with the standard model spectrum, that is just taking the physical standard model particles, you can construct, first of all, the most general 3-point, 4-point, and other contact terms that are consistent just with the standard model that you have, just with the symmetries that you have at low energy, namely baryon and lepton number, electromagnetic charge conservation. And from these, you can construct the most general possible amplitudes. To recover the standard model, you can require perturbative unitarity. So any energy growth is suppressed by lambda to the n. And so this, in principle, gives you either the most general EFT or the standard model EFT with a standard model particle content. And another nice thing about this is that the amplitudes, when written in this way, are correct to all orders or capture all orders in the V over lambda expansion. You can also take a bottom-up approach that does assume SU2 times U1, and that was done, for example, in these papers. Either way, the thing that you need a basis of independent endpoint contact terms. And there are different strategies that people have used for that. Let me talk first of all about massless amplitudes. So the strategy that we've been using in these papers is something that you can think about as a strip and append. So for a given helicity amplitude, you want to separate the structures into a spinor structure times some polynomial in the Lorentz invariance. And then you need to, first of all, find the set of independent spinor structures. Now, since I'm interested in contact terms, I don't want any poles in these. And so, for example, if I have a relation like this between two spinor structures, I cannot use this to eliminate one of them because it would introduce poles, and I want something that's manifestly pole-free. That step is the less trivial step, but it's still easy when you're talking about massless amplitudes. The next step is to just put back the polynomials, multiplying these spinor structures. So these are just polynomials in the Sij's over lambda squared, for example. And these just give the derivative expansion. These are analogous to the derivative expansion of the EFT Lagrangian. And this step is completely trivial. So you can get things up to very high dimensions. Now, for the massless case, the set of independent spinor structures was obtained systematically with a very systematic method for getting them for any n in this paper by Duria and Machado. There are other approaches that people have taken to this, for example, this harmonics approach by Henning and Milia, and using twisters by Folkowski. So let's now turn to massive amplitudes. When we talk about massive amplitudes, I'm going to be using the little group covariant massive spinor formalism introduced by Arkani Hamed et al., where a massive momentum where a massive particle I of momentum p in spin s is described by a pair of massless spinors. So these are these square spinors P, for example, with I equals 1 and 2. And the amplitude would feature two S vectors of these guys, whether these are squares or bracket or angles. And the bold notation indicates that the little group indices are symmetrized over these. And I'll use boldface in general to simply denote massive momentum. One nice thing about this formalism is it's very, very easy to see the high energy limit of the amplitudes. It just corresponds to unbolding, and it's something that I'm going to use very heavily here. So since we're writing the momentum in terms of two massless momenta, in the high energy limit, I can take one of them to scale as m squared over e, and the other one that I'm going to call k to coincide with p. And then the high energy limit of any spinor structure is obtained by simply unbolding it. And this k momentum coincides with p. One thing to note is that the direction, or apart from the fact that we're choosing the magnitude of q to scale as m squared over e, its direction can be chosen arbitrarily, and different choices correspond to different choices of the spin quantization axis. So going back to the construction of the contact terms, again, we use the same strategy. We separate things into a spinor structure times a polynomial. In this case, finding the set of independent spinor structures becomes harder. We refer to these as stripped contact terms because we've stripped off all the polynomials of these. And again, the next step of appending back the polynomials is very trivial. So in order to find this independent set, we rely very heavily on the massless limit. So these massive relations, any massive relations of spinor structures maps to a massless relation, or pretty much almost all of them do. So for example, this massless relation that I showed before is now essentially bolded and receives some mass-suppressed corrections here. So, and this part is the hard part, getting these, completing these massless relations into massive relations is not that easy. One other complication that the masses introduce is that they obscure the dimensions of the corresponding operators. But if you realize that this combination of square and angle brackets, square and angle spinors should be normalized by m, that takes care of this problem. So one way to see this is to know that this is the thing that would appear in a massive polarization. Okay, so using this, we've obtained explicit bases for 3-point amplitudes for any spin, and explicit bases for n equals 4 for 4-point amplitudes for spins up to n, and a recipe for continuing this, but this recipe is not terribly easy to implement. As I said, the hard part is these mass corrections. Now, a very simple byproduct of this is a very simple prescription for getting a basis of spinor structures for generic all n amplitudes, where I do allow non-local relations. And the recipe is very simple. For each combination of contributing external helicities, you want to take the unique massless spinor structure and simply bold it. And that just spans the full basis for the whole amplitude. There is also another approach that was introduced by Dong et al., which is based on the harmonics. And here you want to write amplitudes just in terms of the spinors, just in terms of square spinors and momenta, and then generalize the massless construction. So this gives a complete solution, but the fact that you just use square spinors, for example, obscures the mass dimensions of the different terms, and you also get complicated combinations of structures, so it's not very wieldy. So here I'm just flashing you very quickly the results that the basis that we got for 4-point amplitudes. Okay, so as I said, we use the relations between massless and massive amplitudes very heavily. Let's now take it another step and talk about Higgs EFTs specifically. So here I want to start with massless contact terms and obtain massive contact terms from these. So in a way, we're thinking about the Higgs mechanism in an amplitudes way, which has a very rich history, starting in this paper from 2011, and there were many other papers following that, where these people derived massive Coulomb branch amplitudes for n equals 4 using soft Higgs limits. And then in 2017, there was this paper by Arkani Hamed et al. That has a very different take on the subject and talks about the infrared unification of UV amplitudes. So the massive infrared amplitude essentially unifies different massless UV amplitudes for different polarizations of the external particles. So what we want to do is we want to generalize this to non-supersymmetric theories, and in particular, the standard model. This little group covariant formulation is a nice tool that really simplifies things in this case. And we want to get a detailed understanding of the relation between these two ways of thinking about Higgsing in the amplitude setup. And from this point of view, the EFT amplitudes, namely the contact terms, are very simple objects, so they're a very easy starting point. Okay, so I'm going to assume that the masses originate from Higgsing. So I'm working with masses that are less or equal to V, which is much smaller than lambda, as in the standard model EFT. At low energies, if I look at the low E theory, any endpoint contact term comes with an independent Wilson coefficient, which is not related to lower point couplings. So the number of independent Wilson coefficients is equal to the number of independent, the number of independent contact terms is equal to the number of independent low energy Wilson coefficients, which is also the same as the number of independent high energy Wilson coefficients. So in order to get the set of independent terms, I want to start with the high energy theory, write down all the contact terms, which is easy, and then each one of these will give me a massive contact term. How is this going to happen? So essentially, we'll need to do two things. One is to bold the high energy structures, which amounts to covariantizing with respect to the full massive SU2 little group. And the other thing that we need to do is to freeze the Higgs momentum. So essentially, I'm going to take the Higgs momentum Q and sort of freeze it such that Q plus K, where K is the momentum of another particle in the problem, equals B. Okay, so essentially what we're doing is we're matching the high energy amplitudes and the low energy amplitudes at the scale V. And specifically, we're just looking at the non-factorizable part of the high energy amplitude. So that can be written as a sum of Wilson coefficients times some Lorentz structure. And this Lorentz structure can be divided into a spinor structure that carries the massless little group weights times a polynomial in the Lorentz invariant, which is little group neutral. And bolding this, we're just covariantizing these spinor structures with respect to the massive little group. And then we're matching the leading component in M over E of the massive spinor structure to the high energy structure. Okay, so essentially all you need to do is bold these spinor structures. This is very easy for fermions or transverse vectors. For longitudinal vectors, these correspond to scalars in the high energy theory. So to consistently bold these, the scalar momentum must appear in the high energy amplitude. And so in the high energy amplitude, you have an insertion of the momentum, which simply bolds to this combination of angle and square spinors. That's not surprising because in the high energy theory, this should map into gallstones, which are derivatively coupled, so the momentum should appear. Okay, so let's look at the effects of extra Higgs legs. So as we said above, we relied on the matching of the leading components. So essentially, I'm taking the leading component of this low energy amplitude and matching it to the high energy amplitude. The subleading component in the spinor structures come from amplitudes with extra Higgs legs. So here, for example, is an external fermion with another Higgs leg attached to it. We freeze the Higgs momentum, isolate this pole, and remember that we have to multiply this by V because we're matching an n+1 amplitude to an n-point amplitude at the scale V. So looking at the contribution of this amplitude, you have essentially this VEV that we're multiplying by the propagator, and then this 3-point, which is just the Yukawa, times the blob, which has a factor of eta square for this fermion here. So altogether, you do get the subleading component in the massive spinor structure.
Yael, you have 5 more minutes before question.
Okay, sure. So in principle, to get a low energy endpoint contact term, one way to do this is to start with a high energy 2 endpoint contact term with n extra Higgs legs, such that together their square equals the max squared, and proceed as I described above. Momentum conservation holds all along in this procedure because we're starting from an amplitude with one Higgs leg for each particle that should become massive. In practice, you just need to match the leading component, and you can be more economical about the number of Higgs legs that you can introduce. Okay, so far the Higgsing we saw is completely equivalent to Lorentz. Let's now go to actual Higgsing, which is theory dependent, and look at diagrams with extra Higgs legs that correct the Wilson coefficients. In the high energy theory, we of course have any number of a whole series of contact terms with an increasing number of Higgs legs. When we sum them all up, they will generate the low energy Wilson coefficient as a series in V over lambda, essentially. Of course, not all these contributions are going to be non-zero because of the gauge symmetry. And in the standard model, if AN is non-zero, then the next one is going to be 0, and etc. And if AN starts out being 0, it's typically generated at the next order. Just as the EFT Lagrangian is a function of V plus H, here we see that an amplitude with an external Higgs leg and a Wilson coefficient C will be accompanied by an amplitude with one less Higgs leg and a coefficient V times C. Okay, so let me give a simple example. Suppose you want to calculate the U bar D WH amplitude. So that's fermion vector and scalar. This comes from a number of 4-point and 5-point amplitudes. These exhaust all the structures that you need. For example, in this 4-point amplitude, these are the structures that appear. And so you directly bowl them to get the massive structures. And going on with the remaining amplitudes, you get the full list of spinor structures. So that's all very easy. Specifying to the standard model EFT, you can also match the actual couplings. So here, all I used really is just Lorentz, so it's completely general, but I can also match the specific couplings. So for the specifying to this U bar D WH amplitude, these are my conventions for the standard model fields. I need the following 4-point amplitudes and 5-point amplitudes. And I can look at this one, for example. It has this expansion where these are these polynomials in the Lorentz invariants with a number of Wilson coefficients that appear. And that would give me the low energy Wilson coefficient. Okay, let me just talk very briefly about the standard model contact term as another example. So it's well known that the standard model WWHH amplitude has a contact term suppressed by this. I can get it using bottom-up considerations, but I can also get it top-down, starting with the standard model amplitude at the high energy theory. I can choose my Q momenta for 1 and 2 in such a way that this thing simply translates immediately to the required contact term. Okay, so I'm running out of time, so let me say very briefly that it's the physics of this contact term is very nice. You can see that the Q's in the low energy theory match the high energy reference momenta for the two polarizations. For some choice of either the Q's or these reference momenta, you can get rid of the contact term piece in the Feynman diagram calculation. And what we're doing here is doing exactly the opposite, namely keeping just the contact term. This is looking at the transverse W's, looking instead of the longitudinal W's, the contact term and the low energy factorizable amplitudes both scale is S over mW squared. So the contact term restores perturbative unitarity. And we clearly see the relation between the high energy gauge symmetry and perturbative unitarity. Okay, so since I was out of time, I'm not gonna run through these conclusions. And let me just leave you with this beautiful picture of 4-point contact terms that I mentioned before. Thank you.
Thank you very much. It was a very interesting talk. Do you have any questions for Yael? I guess I had a question while we were waiting for other questions. So one question I had was, so you mentioned that finding relations between the spinor structures in a massive case was difficult. Is it, I mean, can one just try to approach it in a naive way using numerics and ansatz, or is that too complicated in the cases you're interested in? Or
I mean, that's the only way we found to approach it is exactly this naive way. And that's exactly the problem. I mean, we don't have any sort of algorithmic way to solve this. So you just need to try some ansatz and check. And that can be very tedious. And that's precisely the problem. We don't know how to generalize this.
So you suspect there's a better way of doing it, or?
Yeah, I suspect so, but I don't have it.
I guess another question I had is, can you do similar things that you're doing here for the standard model, apply it to gravitational physics? I guess I'm thinking about black holes, scattering, and so on.
Yeah, so I think that's a really good question. I think there has been some work on massive black holes by Routine, for example, and others, and thinking about sort of the most general theories that, or the most general amplitudes from a bottom-up perspective is I think something that's very interesting, but we haven't done anything with gravity so far.
All right, I see no other questions. Yeah, maybe we should thank Yael then and move on to the next talk. So thanks a lot for the nice talk.
Thank you.
And let's move to Ingrid.